So we have two equations here, and we see that W transpose of x is y minus ax minus b, which is very similar to this one. So if I equate these two equations, I can write this equation as uh, W transpose of x plus b is equals to 0. Right, so the two equations are just two different ways of expressing the same thing. For support vector classifier, we use W transport of x plus b, and in this equation here W is the weight vector and b is the bias. So these are the same things which we have already used and explained in a neural network. And so W here is the weight, x is the input vector, and b is the bias term. The name of the variables in the hyperplane equations are w and x, which means they are vectors. So remember that w and x are vectors and not the values. A vector has magnitude, so we saw that the vector has a magnitude and a direction as well, which works perfectly well in 3 or more dimensions. Therefore, the application of vector is used in support vector algorithms. So that's why we say that we have these support vectors in a support vector machine. Okay, so suppose we have two support vectors. One is this one and one is this one here. uh, so one support vector is on the positive example side. Let's suppose we have this x plus here and we have this x minus here. So one support vector is on the positive side and the other one is on the negative side. So we can say that one support vector is x plus, this one, and the other support vector is x minus, which is on the other side of that decision boundary. So if we also have the weight vectors w, which is orthogonal to the decision boundary. Now we have these weight vectors here, and these weight vectors are orthogonal to the decision boundary. So we can say that this is orthogonal to here. Since the support vectors define the margin, to calculate the margin, we can first subtract x plus by x minus. And we have already seen from our definition that support vectors will be defined by their margins, and we want to have the maximum margin, remember. So in order to calculate the margin between the two vectors, we can simply subtract the positive example by the negative example, which means that we can subtract x plus by x minus and perform dot product on the subtracted vector and the unit vector of w. And once I have subtracted x plus by x minus, then I can perform a dot product on the subtracted vector, which is the resultant vector, and the unit vector w. And I have already showed you how we can calculate the unit vector, right? So here you can see that the maximum margin, which is this one, it is being calculated by subtracting the two support vectors. So we have x plus minus x minus here. Now if I write it in the form of equation, we can by using this definition, I confirm its equation. So according to this definition, we are having a dot product of this resultant sum with the unit vector of w, and we have already seen that the unit vector of w can be written as w hat here. So we are taking a dot product of this subtracted value with the unit vector of weight here. So it will become x minus minus x minus dot w hat. Now we have already seen that this unit vector is basically the original vector divided by its magnitude, right? So we can replace this w hat with w by w magnitude, because this term is equals to w hat, which is unit vector. So this equation will become x plus minus x minus dot product w divided by w magnitude. And we have already know from the associated property of vectors that we can write this term as x plus dot this term, which is w divided by w magnitude, minus this one here, and again this x minus and with the dot product of W divided by W magnitude. So we have derived an equation here which can be used to calculate the margin between the vectors. Now, remember that our target is to maximize the margin. So we can define a cost function and gradient updates in order to maximize the margin, and this will be equivalent to minimizing the loss function. So you remember that in neural networks we have seen that our ultimate target is basically to minimize the loss, and by minimizing the loss we are making sure that we are improving the accuracy of the network. Similarly, here maximizing the margin means that on the other hand we are basically minimizing the loss. So we can define a loss function. So once we have this loss function minimized, it means that we have the margin between the vectors, it is maximized, right? So this is the objective function, you can say. In the SVM algorithm, we are looking to maximize the margin between the data points and the hyperplane. So I have told so many times that this is the thing which we are looking for in a support vector machine. So normally the loss function which is used in a support vector machine in order to maximize the margin is a hinge loss function. So we can define this loss function as the maximum of this W transpose of X plus B. So this is the same term which we have derived in the previous slide, and we see here that this is the weight, this is the input vector, and this is the bias term. So our loss function basically consists of this term here, and we are basically looking for maximizing the maximum function here. And as a regularizer, we can add a lambda term here, which will be used, which will the function of the regularizer is very similar as we have discussed during the neural networks lecture. So this lambda term can be defined as lambda is equals to 1 over c, where c is always used as a regularization coefficient. And I hope you have also practiced on the Google Playground. You have seen that as a regularization coefficient we have different values. So we treat this regularization as a hyperparameter. Similarly, this is treated as a hyperparameter again in SVM, and we look for a coefficient here which helps us to obtain the required objective function. The function of the first term, this term is a hinge loss function, and it helps to penalize the misclassification, because if we are penalizing the misclassification, then over the period of time we are basically reducing that. It measures the error due to misclassification. So the purpose of this loss function is to determine the error which is being occurred due to the misclassification. And you know, here misclassification are the data points which are being closer to the classification boundary than the margin. So we are treating them as the misclassifications here. The second term is the regularization term, which is a technique to avoid overfitting by penalizing large coefficient in the solution vector. So as I told you, that very similar to the neural network, the purpose of the regularization term is to avoid the network to go towards the overfitting, because with overfitting, if our network is prone to overfitting, then on the test data the accuracy will be reduced. So similarly, in support vector machine, the regularization term helps to reduce the overfitting by penalizing large coefficients. And here the lambda is the regularization coefficient, and its major role is to determine the trade-off between increasing the margin size and ensuring that I lies on the correct side of the margin, right? So if we understand it with its graph, so you can see that the hinge function can be described here with the fact that the error is 0 here if the data point is classified correctly, right? So if the data point is classified correctly, it means that we don't have any misclassification, and that's why with the error is 0, and we have a correct classification. When the true class is -1, the hinge loss looks like this in the graph. So for the class -1, it will be similar to like this one, and we need to minimize the above loss function. So the target is to minimize the loss function in order to maximize the maximum margin classifier.